only like 2 weeks of exams, just not worth going back to jail. Not a chance.
Okay, I guess we can get started. So I just make it like this, so if someone gets into the room, I can just let them in. Okay, so today we are going to the phase of organic pollutant. So we are going to a new unit. And so for this unit, for this lecture, we still have 6 points. And so first, I would like to introduce some of the significance of organic pollutants and POP, which refers to persistent organic pollutants. And then I would like to do some brief review about the relation between chemical structure and their their properties, because the property of a chemical determines its partitioning in the environment. And then for the next 4 points, I would like to talk about the partitioning of the organic pollutant between pure phase and air, pure phase and water, air and water, organic solvent, and water. So first, let's take a look at the some general ideas. So basically, like from chemical engineering to toxicologist. So I guess this can be chemical engineer. So basically, we know that for a chemical, they are invented by the chemical engineer. And then if we are using this chemical, and these chemicals may be released or emitted into the environment. And in the environment, it will do the partitioning. So we know it has some concentrations at different mediums, like in water, in air, in soil, and in the biota. And I think in this course, we did not talk about like the partitioning in water a lot, or the modeling in water a lot. But I think in Fall2021, I think the instructor is Dr. Davis or Travis. I think in that course, Fall2021, we talk about lots of models in the water. So anyway, if the chemicals in the environment, then we can know their exposure, and then we can use the knowledge of those effect interaction. We can determine its impact or interaction between the chemicals and the environment and or the animals or human beings. And for most of these processes, we use models. And for environmental engineer or environmental engineering, we focus on these 3 processes. So here shows the leading environmental pollutant. So basically, we have silt, nutrient, metals, toxic organic chemicals, pathogens, and organic matters. So like when I was young, I was very confused because for the nutrient, I think nutrient is good. So why it is an environmental pollutant? But we know that like for the ecosystem, nutrients may have the problem of eutrophication. So basically, if we have an ecosystem and if we have lots of nutrients, and then some of the species will be favorable of these nutrients, so the amount of that species will be overwhelmed. So as a result, we only have a small number of species. So basically, in the environment, we want to have different species, so we can go to the field and we can catch different species efficiently. But if in the environment we only have a few number of species, we are not very happy and it is not fun to go to that field. So eutrophication is a problem. Here we can see that they have some overlaps, like for the nutrients or toxic organic chemicals. They are also, like some of them are also organic matters. Then I would like to talk more about organic pollutants. And here are some classifications. And the first one is like some of the chemicals, they are persistent, bioaccumulative, and they are toxic. And here are some examples of these chemicals. And we also have like emerging contaminants. And again, here are some of the examples. So we just need to have some general ideas about these chemicals, like about which classification they belong to. And we also have some biogenetic substance, like these ones. So here I show some example, which is endocrine disruptor. So many of the organic chemicals, they are endoric disruptors because they have the similar structure with the hormone. We know that in human or in animals, we use hormone to transmit information. And then for the cell, it can receive this information by using the hormone receptor. But for these organic chemicals, like some of them have very similar structure with the hormone. So they can also attach to the receptor. But because they are persistent, so our body cannot remove them from the receptor, which means it's just standing on that position, and then the cell will just lose its function, so which is very bad. And because of this effect, many of these chemicals have some chronic and toxicity effect. Then more about POP. POP refers to the persistent organic pollutant. So this is also part of the organic pollutant. They have some properties, and according to its name, it is persistent, which means they are very difficult to be degraded. So they can remain in the environment for a long period of time. And they can also become widely distributed through the environment because they have different species and they have like slightly different chemical or physical properties. And they are also bioaccumulative because they are organic. And so they can be accumulated in organisms. And they have the deleterious effect on human and animal health and the environment. So because they are toxic. And we know that like the lab I am working for, like is the Persistent Organic Pollutant Research Laboratories. And this is its logo. And its logo, we know that it is phenolphthalein. And as I mentioned before, we have in the air, the pollutant in the water, the pollutant in the soil, and the pollutant in the biota. But I want to say this is very different from my original design. I can share my original designs with you guys. So it is something like this. Yeah, so this is my original design. For the air, I want to emphasize the dispersion of the air pollutants. And this is a Gaussian plume model, which I will discuss in the air pollution lecture. And in the soil and in the biota, actually, I wanted to add more details, like for the equations and the chemicals. And for the pollutant in water, I want to show the process of water purification. So we have the dirty water here, and we have the clean water here. And finally, we can drink the water. But they just simplify into this. So, but it's okay.
You're a really good artist. Yeah, you're
Thank you.
cool.
Yeah, I like painting, so I buy the iPad. Yes. So here are some important items here. So basically, because of the pollution of the POPs, we have the Stockholm Convention. And I want to emphasize that in this convention, we limited the use of DDT because DDT is a pesticide and it is toxic. I will talk about DDT here. So here are also some other historical events. Like for DDT, it was widely used in 1940s to 1960s. and now it is banned. So in this class, I will talk more about DDT in the future lectures. So DDT is an important chemical in this class, and because I'm also doing research on this chemical. Another one is PCB. It is a low flammable oil, and it is also widely distributed in the environment. Like it's usually used to, I think, to cool down the voltage changer, like something like that, because it is non-flammable, so it can be working with very high temperature stuffs. But now it is banned. And here shows the chemical structure of DDT and PCB. We can see that they have some benzene rings, which makes it stable. And it also have like chlorine attached to it. Based on the organic chemistry, we know that if we have this chlorine attached to the benzene ring, it can make the structure more stable. So they are pretty persistent. And we also have two books talking about the environmental impact of DDT and PCB. And here shows a picture. This is the old picture, and we can see that when DDT was first released, it was believed to be a non-toxic. We can see it is powerful insecticide, and it is harmless to humans. But now we know it is toxic. Yeah. And we have a kid standing in the plume. Yeah, so I think the implication of this picture is that even now we have some pesticides or pharmaceutical stuffs which is advertised to be harmless, but maybe in future they will be toxic, like their toxicity will be identified. So for now, when we are using a pesticide, we can just don't do this, even though they are called to be harmless. Okay, anyway, so DDT also have some impact to the environment. We can see that the eggshells will be thinning by DDT. Like when we have DDT in the environment, and it will be accumulative in the bird. And when the bird has eggs, so usually we will have the egg, which is good. But if the bird is exposed to DDT, then the shell of the egg will become very thin and very crispy, so they will be easy to be broken, so which is bad. And we also have some other events, so I'm not going through them one by one. So far, do you guys have any questions? No? Okay. And the next one, I would like to do some brief review about chemical structures, especially in the organic chemistry. So I hope every one of you know functional groups, which is an important concept in organic chemistry. So a functional group is a special cluster of atoms that performs a useful function. And most of the useful behaviors of organic compounds comes from their functional groups attached to the carbon. So if we are familiar with the properties of the functional groups, and then we can guess the properties of the organic pollutant. And here I emphasized 4 functional groups. The first one is haloalkane, so which is like FCl, BRNI, but in the environment, we usually have the chlorinated organic pollutant. And also, we have alcohol, and this carboxylic acid, and this amine. So I will go through them one by one, except for the first one. So for the hydroxyl group, it is a functional group with the chemical formula like OH, and the composites of one oxygen atom covalently bonded with one hydrogen atom. So let's focus on its properties. So this functional group usually do not dissociate H+ in water, but except for the carboxyl group, which I will discuss in the next slide. And for this functional group, it can make the small organic molecules soluble, or to be more accurate, it can increase the solubility of an organic chemical. And here are two examples of the organic chemical that has this hydroxyl group. And this is phenol, and this is phenolphthalein, which we are very familiar with. And the next one is carboxylic acid and carboxylic group, so which is COOH, and the structure is this. Not this one, this is acetic acid. So a carboxylic acid is an organic acid that contains a carboxyl group attached to the R group. And the general formula of carboxylic acid is this one. So again, let's look at its properties. So this usually dissociates H+ in the water, so it can make the organic pollutant performs as an acid, but usually this is weak, so it can be considered as a weak acid. And then this functional group can make the organic molecules soluble. Or again, it can increase the solubility of the organic chemical. And here are some examples of the organic chemical that has this functional group. And here I put a star, because for vitamin C we know that it is acidic, but it doesn't show this functional group on it. This is because it has a conjugate structure, so it will change the form into the form that has this group. So vitamin C is a special case. Another one is amine and amine group. So this is a compound and functional groups that condense basic nitrogen atom with a lone pair. And amines are formally derived of ammonia. So we are familiar with ammonia, and ammonia, we know that it is a base, and it is soluble in water. And it can have the chemical structure plus H2O to form this one. So this is this is quite soluble in water, and it can make the water become basic. Similarly, if we replace this hydrogen, into some R groups, and then we can have different types of amines. So again, amine can make the organic molecules soluble. So far, do you guys have any questions? Okay, that's good. And then we are going to talk about the partitioning between different phases. And so the first one is vapor pressure. So some people use like P O or P0 as the superscript, but sometimes we use the P0 as the subscript. So it doesn't matter, you guys can choose which one you like. So for the vapor pressure, it is the partitioning coefficient between pure, solid, or liquid phase and the gas phase. So the vapor pressure is defined as a pressure exerted by a vapor in a thermodynamically equilibrium with its condensed phases at a given temperature in a closed system. So the keyword is equilibrium. It must be at equilibrium. So vapor pressure controls the concentration in the air in equilibrium with the pure phase. And it is usually increased with temperature. So if we boil the water, and more water will, if we increase the temperature of the air, then the air can contain more water vapor in its body. So let's look at like some trend of the vapor pressure. And this shows the vapor pressure of different chemicals. And we can see from this picture, what conclusions can you guys get? Does anyone want to talk about this?
There's a very large range. There's a very large range. They're not all consistent.
Yes. Yes, we can see it has a very large range. But I also want to say, let me just show example. For example, this is benzene, and this is a benzene with a long chain. We can see that with the chain increase, like the length of the chain increase, its vapor pressure decreases. Right? So how about this one? Do anyone want to talk about this?
Yeah, so generally speaking, as either more benzene rings or more chains are added, like in the case of chlorinated benzenes, as less chlorines are added to the benzene ring, you can maintain a higher vapor pressure compared to one with more chlorine along with benzene ring.
Yeah, we can like more chlorine and smaller vapor pressure, right? And it is intuitively making sense because if we have more chlorine attached to it, it is heavier, so it is harder to get to fly. And so similar for this one, we have more chlorine, and it is harder to fly. And similar for this one. So basically, we can see that the vapor pressure is related to the mass of the molecule. So for this one, do you guys have any questions? No? Now let's look at an example. So let's say in a factory in which the metal parts are degreased with organic solvent, and somebody drops a glass container containing 10 liters of the trichloroethane, like TRI, like this one. So in the closed room at 20 Celsius degree, and the room has a total volume of 50 cubic meter, and the bottle breaks, and the solvent mixture spills on the floor, and soon one can smell the solvent vapor in the air, and because this is due to dispersion. So we have a question: do we need to evacuate people in that room? And to answer this question, we can split this question into three small questions, like what processes are involved in this event? And to answer this question, what information do we need, and where we can find the reliable information? So I want to talk about the first one. So do you guys think what processes are involved in this event? Like I break up someone in the lab and holding a bottle, and then this bottle breaks. And then what happened?
The gas disperses throughout the room and starts evaporating.
Yes. So first the liquid or the things in the bottle will just spill, and then it will be dispersed in the room. So we have like these three processes. And to answer this question, do you guys think what information do we need? Yes.
Well, we need to know the toxic concentration, or the minimum concentration needs to be toxic to people.
Yes. So this is toxicity reference value, right? Which we discussed in lab 5. And do you guys think more information do we need?
You need to know the vapor pressure, and then how much of the material material was spilled and how big the room is and the information that we already have.
How big is what?
How big the room is and
Yes, we know the room.
yeah.
Yeah.
But
And
like that, yeah, I'm just saying like that's
yes.
information you.
So you
it's
mean
useful
mass?
information.
Yeah. And you mean mass? I guess you mean like the molecular weight.
Mm-hmm.
Yeah. And more things. Like when we talk about a chemical, and we assume it is spilled in the ground, and we assume it will evaporate in the air. So do we miss something?
Boiling point?
Because
Like the boiling point of it?
yes,
So the temperature of the floor.
yes. So we need to know the boiling point and the melting point because we want to know what's the state of this chemical. So I think that's most about it. Another question is where we can find this reliable information. Do you guys?
Shouldn't it be like on the bottle? Like if there's a chemical, there should be like a bunch of information on the bottle
Oh.
and the container itself.
Yeah, that's a good idea. But yeah, but I would assume sometimes because the bottle breaks, we can. Yeah, I guess after this lecture, I will combine these two videos together. Okay, anyway, so. So we can find the information here. And then by collecting all the information, for example, this is the information that I collected. So, like we have the molecular weight, and we also need its density, yeah, and its boiling and melting point, and the vapor pressure. And as you said, we need the toxicity reference value, and the toxicity reference value I found is like 8% of the saturation at its limit of the vapor pressure. So in this case, first we know that it is a liquid, and we know its density. So, and because we know its volume, so we can calculate its moles. So basically, we use the mole equals to the mass divided by the molecular weight. Oops. And the mass equals to the volume times its density. So this equation describes these two equations. And finally, we can get its moles, which is 100 moles. And then we want to know if what's the mass needed to saturate this whole room. So we can assume this room is at saturation. And at saturation, we can see here, so the concentration of the air equals to the P, like the vapor pressure divided by RT. And this formula is derived from here. So basically, we know that the ideal gas state equation is PV equals to RNT. And then we can remove, let me see. We can remove N divided by V, which is a concentration, and this equals to P divided by RT. And then we can have this relation. So we can calculate the concentration of TRI in the air when it is saturated. And then we can just plug in the numbers. We can have this one, and then we can get the concentration in the air when it is saturated. And then we can use the moles of the TRV in the air. It can be calculated by using the volume times the concentration. And we know that the volume of the room is this one, and the concentration is this one. So we can calculate the moles in the room when it is saturated. And we can see that this number is larger than this one, which means if we have all of the chemicals in the air, like the air can contain all of these chemicals. And we can also see that 111.1 is greater than 8% of its saturation, which means evacuation is needed. And we can also calculate the concentration of TRV in the air, which is this one. So for this example, do you guys have any questions? No? Okay, that's good. And actually, this is a undergraduate level of the question, but we know that, I guess also in the 212, we know that when the gas evaporates, like the concentration will change like this. Like if we assume the room is a batch reactor, like it is completely mixing, we know that this is a time and this is a concentration. The concentration will finally get to this one, but it will just gradually increase. So in this case, we know that we have some time at like 8%. This is TRV. So we have some time for people to get out, and we can calculate this time if we know the dynamics of these evaporation processes. Okay, so let's look at another one, which is aqueous solubility. And this describes the partitioning between the pure liquids or solid and the saturated aqueous solution. And it is usually noted as CW. And so for the aqueous solubility is the concentration of the chemical in the aqueous phase when the solution is in equilibrium. Again, it should be in equilibrium with the pure compound in its usual phase at a specified temperature and pressure. And in the environmental science, the temperature is usually 20, and the atmosphere pressure is usually 1 atm. And so let's look at some of the properties. So first, it is moderately temperature dependent. And we know that sometimes we use insoluble or like soluble to describe the chemical, but they are qualitative descriptions. So in environmental science, we usually just give its solubility, which we want to describe it quantitatively. Also, it describes whether an organic compound likes or dislikes the water. And we know that it depends on the functional groups. So if we have the functional groups like this, and this, then its water solubility will be increased. And here also shows the water solubility of the chemicals change with its structure. From this figure, we can also see that, again, if the compound has a longer chain, then its solubility will decrease. And if we have more chlorine attached to it, and then its solubility will also decrease. And similarly, like as it becomes very large, the solubility decreases. So basically, for smaller molecules, the solubility usually larger. So for this one, do you guys have any questions? No? Okay. And the first one is partitioning between air and water. And we use Henry's constant to describe this partitioning. So at a constant temperature, the mass of a gas dissolved in a given volume of the solvent is directly proportional to its partial pressure in the gas phase in equilibrium with its solution. And so Henry's constant is defined as the partial pressure of the chemical in the air divided by the concentration of the chemical usually in the water phase. And in this case, Pg is the partial pressure of a chemical, and the Cw is the concentration of the chemical. But in practice, we usually have the Henry's constants of different units. Like the ATM can be changed into Pascal or bar. And for the concentration, we may have the mass. So it doesn't matter. We just need to know that give the unspecified unit, the Henry's constant will not change. But usually I prefer this unit because ATM is like around 1 in the environmental science, which can simplify the calculation processes. And usually when we do the calculation, we use the ideal gas state equation, PV equals to RNT, and to do the unit conversion. And again, here shows the chemical structure and change with Henry's, like the Henry's constant change with chemical structure. Again, we can see that for this one, so this shows different chemical bonds. And for this one, is a little bit interesting. We can see that this one has a longer chain. This one has no chain. But for the longer chain, it has larger Henry's constant. Larger Henry's constant, which means that it prefers water, it prefers air than water. Do you guys think why this happened? Because we know that this one is heavier than this one, but it's prefer to stay in the air. So basically, because if we have this long chain, actually the water is hard to attach to it, so it will be repelled by the water molecule easily than this one. So the water will just repel it from the water into the air. And similarly, we have like the trend of this one, of these different chemicals. We know that like for this one, we know that it prefers stay in the organic phase. It doesn't like either air or in the water. So like they have the change is relatively small. So for the Henry's constant, do you guys have any questions? Yes.
For the hydrocarbons down the bottom, why is the C18 has a much smaller Henry's constant than C10, but then C5 is in the middle? Why is that?
Yeah, this is a good question. So basically, the Henry's constant is like as the mass increase, KH, as the mass increase, it's something like this. No. So this is mass, so it is something like this. So for the larger mass, it either prefers to stay in the water and either to stay in the air. But in a small molecule, it is in the middle. Yeah, that's a good question. I haven't think about that before. But I will try to answer this question. I will figure it out. Yeah, that's a good question. Okay, so any more questions? Yes.
So the longer chains make it more that the Henry's constant is higher when it has the longer chains, but then when it has more chlorines.
You mean
like with the chlorinated benzene?
This one?
Polychlorinated.
This one?
Yeah, that or the one below it. Why doesn't the chlorine behave the same way as the chain?
Can you say that again?
Why doesn't the additional chlorines don't behave in the same way as the longer chains?
Oh.
Because in one of the previous examples you showed it had.
You mean this one?
Yes.
So for this one, it shows more chlorine. It prefers to stay in the. It prefers not to stay in the water.
Okay.
More chlorine, less like water. And for this one, more chlorine, less like water. Yeah. Yes.
I think Zoom disconnected, so I think you might be muted and not sharing screen.
Oh.
disconnect. Like, I think this meeting got shut down.
Oh.
Because all of them, the things just disappear from the side.
Maybe that's restart the meeting. I guess that's the internet issue.
Because everyone was there right before it shut off.
Yeah.
I think they were all just kicked off the meeting when it shut down.
Yeah, but luckily I recorded this, so. Okay. So yeah, I will figure this out. I think this is a good question. I haven't think about before. And I think we have the last one. So I'm not sure if they can attend. But so the last one is octagonal water partitioning coefficient. And this is a coefficient between the chemicals in the octagonal phase and the water phase at equilibrium. So, like this is the concentration of the chemical in the octagonal, and this is the concentration of chemical in the water. And this is the most common way of expressing the lipophility, right? Lipophilicity of a compound. So here I want to ask a question of why octane, but because of time, I just answer it because it is similar to the fat of our body. Like it has very similar chemical properties. And so for this one, do you guys have questions? No? Yeah, okay, nobody comes. But let me just. Okay. So here's a summary. So if we know the partitioning coefficient, either by experiment or by theoretical modeling, and then if we also know the total amount of the pollutant in the environment, and the pollutant usually released in only one phase, so we can count its total mass, and then we can calculate the pollutant concentration in each phase when in equilibrium. So suppose we have the chemical released as a pure phase, and we know the vapor pressure, and we know the solubility. So we can calculate the concentration in water and in air. And we also know QW. So we know its concentration between the biota and water. So basically, we can know its concentration at every phases, theoretically. So here I just want to say that as a master level environmental engineering student, like we usually have ENCE411. So if you guys go to graduate school here, you may select this course, and this course is the environmental organic chemistry. So basically, we want to, like when we see the chemical structure of an organic chemical, and then we can guess or speculate its properties. And by knowing the properties of the chemical, then we can speculate or guess its environmental fate of that chemical. So although we need to know that, we need to have that ability, but in practice, we can usually find the properties of the chemical, like from the handbook or from the internet. For example, here is a summary table of the different properties of like this organic pollutant or pesticide. And here, KOC refers to the partitioning between water and soil organic matter, because we know that soil is coated with organic matters. So here again, I want to have a question, like for DDT, and we know its solubility log KOW, and its vapor pressure and molecular weight. The question is like, where do you expect DDT to have a high concentration in the environment? How do you guys think? Or I guess because like we are not familiar with the properties of other chemicals. So, but here I want to say, because this is log, which means the KOW is like 10.6.91. So this value is pretty large, which means that it is very soluble in the organic phase, which means the DDT will be accumulated in the biota. And on the other hand, because this is soil organic matter, this is also pretty large. So DDT is also likely to stay in the soil. And this is what we have now. Like for the contaminated site, for the DDT contaminated site, the DDT are mostly stay in the soil because the soil has a very large volume. And we can also see that the vapor pressure is pretty small, and the solubility is also relatively small. So DDT are usually stay in the biota. So far, do you guys have any questions? No? Okay, I think that's it. So because of time, I'm not going through all of this, but here I just want to emphasize one point, which is the solubility, aqueous solubility. Do you guys think what with temperature? Increase or decrease? What?
It's a moderate increase.
Minor increase? So most of you guys think it is increase. So the actual answer I want to say is depends. Because this picture shows the solubility and the temperature. We can see that for some of the chemical, solubility increase with temperature. But for some of the chemical, the solubility decrease with temperature. So the solubility and the temperature has a complex relation. So I just want to emphasize it just depends, not increase or decrease. And again, here are some notes. So basically tomorrow we will have this seminar, and I recommend you guys to join and you make it the extra credit. But don't forget to post your ideas on the discussion. And on Thursday, we will not have class. So originally my plan was, because the deadline of assignment 5 is this Friday, but Shazad just suggests to give you guys one more week to finish assignment. So, but for now I do not want to change my plan. So on Thursday, you guys can work together to finish this assignment. And that's it.